All right, good afternoon, everyone. Let's continue the discussion about resistor applications. So let's see. All right, so we had looked at resistor applications in a voltage divider network. All of these follow the same principle. Okay, we have two or more resistors connected in series, apply a voltage to a series connection of resistors, current passes through all of those, current remains the same, but voltage gets divided. In most circuits, we'll use a minimum of two. Obviously, we can't have less than two resistors, but I'm saying most of these circuits just require two resistors to create a separate output voltage based on the input voltage that we're applying, right? And so here I had an example of we had 9 resistors connected to a 9-volt source. But let's look at a more practical application where we have a transistor, and the transistor has two resistors. The two resistors create a voltage divider network, right? So this is, I think, where we had stopped. We had covered a little bit of the next slide also. So any questions before I proceed? Okay. The app, yes. Yes. Mhm. Yeah. So what was I saying? Oh, the application is different, but the principle is exactly the same. Voltage gets divided across these resistors. So here is the op amp. Op amp has or needs a biasing circuit, and so we use a voltage divider bias circuit. And we'll see that in the next couple of slides, the equation that governs this. Okay. One of the other areas where we see this is in the oscilloscope probe. So if you look at the place or the connector that connects directly into the oscilloscope, there is a visible bulge. It is quite large compared to a standard connector, and that bulge has a circuit like this inside it. Okay, that allows us to step down the voltage that is fed into the oscilloscope. So we could feed 100 volts at the tip of the probe. At the other end of the probe, where the connector is, that connector steps it down to 0.1. So that 100 volts is now only 10 volts. So the oscilloscope only sees 10 volts. But in the oscilloscope settings, we need to ensure that we set the probe settings to 10:1. So the oscilloscope knows that whatever it measures needs to be multiplied by 10. Otherwise, we get an incorrect reading. Okay. That's some practical considerations to keep in mind. All right, voltage summation using resistors, weighted voltage summation. Okay, so we have a circuit right here comprised of two voltages, V1 and V2, and we wish to add them together. So V out is at this point. And in this case, the resistor values are different because we want to add them in a 2:1 ratio. Okay, so what it is a simple voltage divider circuit like this. It's V out here, that's V1, that's R1, and that's R2. So if I was to solve this using superposition, in superposition, I have V1 operational at a time. So when V1 is on, V2 is off, V2 is replaced with a short circuit, meaning R2 gets connected to ground or the negative end of that supply. And so we get a circuit like this. In this case, V out is going to be V1 times R2 or R1 plus R2. And then when V1 is off and V2 is on, I have a circuit that looks like this. And now my V out is here. Okay. V out is here. And this is V2. This is R2. This is R1. Is it different or is it the same? Oh, sorry, this is R2. Now, are there any differences between the two circuits? Sorry, can you repeat that? Absolutely, yeah. But the circuit is still the same. Okay, both circuits are the same. They're effectively connected. So V1 with R1 and V2 with R2, they're in series. So voltage source in series with a resistor, but those branches are in parallel together. So if one of the sources is off and the other source is on, then as was pointed out, V out is across R2 in the first one. And the second one, still the same, but it's across R1. It's just drawn a little bit differently, that's all. It's still a series connection. So if I turn it around, I can do this. R2, R1, plus minus right here. And then I have my V out 2 on this side. Okay, so V out 2 in this case is going to be V2 times R1 or R1 plus R2. And superposition, of course, dictates that V out is the sum of the two voltages. So actual V out is V out 1 plus V out 2. Okay, and thus we obtain this equation from superposition. Okay, now we want to add them in a ratio of 2:1, right? So we want V2, we want output V2 to be twice as much as V1. So if we take the ratio of V2 to V1, that should result in 2. That's our design, that's our design criteria. So if we take V out 2 over V out 1, we can take V out 2 over V out 1. We can obtain a ratio of 2 for R1 and R2. That means R1 must be twice R2. Twice R2. So no matter what value we choose for R2, R1 must be 2 times or double the value of R2. Okay. Let's take a pause, think over that. Let me know if you have any questions. It's a slightly different kind of application, but the principle is still the same. Okay. All right. Okay. All right. Voltage summation in electronics. One of the things, as I mentioned in last class, is op-amp is a device that is created from a circuit comprising of numerous transistors and resistors and a few other components, primarily transistors and resistors. That's not something that we look at until you get to higher level, 300 level E classes, even 400 level actually. But in the first year, 100 level, we do teach students how to use op-amp as a building block. So it's an off-the-shelf component. We take that off-the-shelf component and we create circuits using that. Okay. So an op-amp or an operational amplifier is noted by a large triangle like this. It has an output. V out is taken there. This is the inverting and this is the non-inverting terminal. At the inverting terminal, we have an input resistor. We call it Ri. And then we have a feedback resistor called Rf. It feeds a little bit of the output back into the input. So this is V minus, this is V plus. And so that's what's not shown here. Okay. But Ri and Rf together, they form a voltage divider network. Okay, voltage divider network. Exactly the same thing as we saw previously. Okay, a fraction of the output is fed back into the input. So the inverting terminal, which is V minus, receives that voltage. And simply by changing the ratio of these resistors, we can get an amplified version of the input at the output. And that is the fundamental operating principle of a amplifier circuit using an op-amp chip. Is there an op-amp in a lab kit? Is there? No? Okay. All right. Okay. All right. Mixed component voltage summers. Well, this goes back to the transistor application. We have a voltage divider circuit creating a biasing voltage for the base of the transistor. And then, of course, we find the Thevenin equivalent circuit as seen by the base. Actually, I don't need that. And this is A and B. We can describe this as plus minus 12 volts. And this goes into the base. And you get Thevenin voltage and Thevenin resistance. As seen previously, this Thevenin voltage is 1.83 volts, and this Thevenin resistance is 3 kilo ohms, right? And this is connected into the transistor. So simply by using multiple resistors, we can have voltages in any value we want. Okay. You might want to note and mark this because this will come up again in 315. Has registration already begun? Or is it a couple of more weeks? 2 more weeks, okay. Okay. Well, you all have to take 215, so there's enough slots for that. All right. Oh. Writing. Okay. R2R ladder networks. Okay. This kind of circuit is known as a ladder network or ladder circuit. Think of it as it lying on its side, and you can see multiple steps and rungs on that ladder, right? Now, it's comprised of 8 resistors in this case. They're either, you'll see from the analysis, they will turn out to be either in series or in parallel. If you look at the far right of the circuit, you will see 2 resistors in parallel. All of the resistors that are vertical, they're all 2R, and all of the resistors that are horizontal are value R. Doesn't matter what that value is, just suffice to say that they're all the same. Okay. And then 2R, of course, just twice as much as R. Okay, so if you look at the far right, what do you see? You have 2 resistors in parallel, both with a value of 2R. So what is the REQ of those 2 resistors? Just R, right? Also, just as a sidebar, for N resistors in parallel, all with the value R, the total REQ is R divided by N, R over N. If you have 200 ohm resistors in parallel, it's 100 divided by 2. So REQ is 50. If you have 10 100 ohm resistors in parallel, it's 100 divided by 10. If you have 100 100 ohm resistors in parallel, it's 100 divided by 100. Total REQ is, well, 50, 10, and 1 case. Okay. So if you have 2 resistors in parallel, we start at the far right. We can obtain one single resistor R. And this R is then in series with this, right? Because that's a pathway to ground. This R is 2R in parallel with 2R. And the series connection, R plus R gives me 2R again. So going forward, this 2R and R is R, along with this in series gives me 2R, is then in parallel with 2R, again gives me R, R plus R, 2R, 2R and 2R in parallel, and again finally R plus 2R, so 2R and 2R in parallel. And that's how you reduce the circuit, starting from the very right, moving towards the left. But now let's look at what happens with the current. Because the current comes in from your source, immediately encounters 2 equal resistances. Okay, so it splits into 2 equal parts. We know there are 8 resistors, so it needs to divide 4 times. So we start with a number of 16 just for explanation purposes. But the point here is that whatever current is coming from the source gets divided into 2 equal parts. One is going down 2R, the other one is going to the rest of the circuit. And so 16I gets divided into 8I and 8I. Okay. 8I then gets further divided into 4 and 4. 4 gets divided into 2 and 2, which gets divided finally into 1 and 1. Okay. This kind of circuit where current division is taking place, binary current division is taking place at every single step. It's being divided into two equal parts. Okay. This kind of network is known as a ladder network. Okay. Ladder network. The notations here with the arrows are simply showing what the REQ is when you look into the circuit from this angle, meaning when you're measuring from this point. Okay. So if you combine these two together and you find REQ at these 2 points going here, that would give you a value of R. And then 2R, 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 and then finally R. Okay. That's what it means. Application for this one is typically in electronics, more commonly in digital to analog converters. That's something that you look at the tail end of 315. Okay, tail end in 315. But for now, again, we are simply talking about resistors and the applications of resistors. And so this is, again, current limiting and voltage division. Right? Okay. Let's talk about an application of LEDs. LEDs are light emitting diodes. These are semiconductor devices where you apply a voltage okay. Diodes are one-way devices. There's two terminals, A for anode and K for cathode. The names diode, anode, and cathode are a holdover from the vacuum tube era, or not a holdover, but they were brought over from the vacuum tube. So we had vacuum tube diodes. Those had two electrodes. So diode literally means two electrodes. And this is a semiconductor version of the vacuum tube diode. The name of the nomenclature carried over, and vacuum tube diode was the name given to a regular, so the diode was the name given to a solid state version created from semiconductors. So even though they don't have any electrodes, the name still stuck, and we still call them anode and cathode. Okay, technically the names come from electrodes, the polarizing electrodes. Anyway, diodes are one-way devices. Diode voltage is always measured with a positive reference at the anode and negative at the cathode. And current always flows from anode to cathode. And I believe I've talked about this. When you have arrows coming out of a diode, it's emitting light, meaning it's a light emitting diode, LEDs. If there are arrows coming into the diode, it's a photodiode, like a solar cell. Okay, so it senses light and converts into electrical energy. Okay, so if we look at this example, if we are given the specs for this LED, so given specs are that the diode requires 0.9 volts to 1.9 volts to turn on, and a maximum of 20 milliamps of current flowing through it. The diode characteristics look like this. Okay, so the LED characteristics look like this. And because it can only take a maximum of 20 volts, 20 milliamps, We don't want to exceed that current. So the question here is, if you have two batteries connected in series, which means we have a total of 3 volts available to us, how can we step down the 3 volts to 1.9? And how can we limit the current? Okay. And so a simple design circuit, we put a resistor in the middle. The resistor is in series with the diode. So whatever current is coming from the source goes to the resistor and it goes to the LED. So first thing we can do is we can apply a KVL equation around the loop. 3 volts has to drop across the diode as well as the resistor. VR plus VLED or VD. Either way, it doesn't really matter. You're supplying 3 volts from your batteries, goes into the resistor and into the diode. .1 volts. So from applying KVL, if you want to limit the voltage across the diode to 1.9 volts, then the resistor must drop 1 volts across it. Also, the resulting current cannot be more than 20 milliamps. Let's take a pause while you think over that. Let me know if you have any questions. So far, so good. Okay. So we applied KVL. Now all that's left to do is apply Ohm's law. Ohm's law gives me VR is equal to I times R. Which turns out to be equal to approximately 55, 56 ohms. Okay. Let's take a pause. Yes. Where? In dot in the middle of the actual value. Okay. Oh, that one is 1.1. Yes. That's the voltage value. Yeah, 1.1 that we obtained from above. By applying KVL in the first step. It's already, so it was part of the problem statement. Okay, so anyone have a coin battery at home? A coin cell or a button cell, you know what I'm talking about, right? Those are the smaller button cells are about 1.5 volts, I believe, and the coin cells are 3 volts. You have LEDs in your lab kit. You want to do a small experiment at home, you take one of these LEDs and you stick it across, let's say, if this is the coin cell, you take the LED, take the positive, anode and just slide the coin cell between the two terminals and press down on them so that they are making contact, and the LED should turn on. We don't need to have a resistor for those kind of circuits because the battery is so small that the current that is supplied from that battery is going to be very small. But it might be sufficient, just sufficient enough to turn the LED on. Okay. As I said, it's 3 volts. You're applying 3 volts. It's going to source some current, but you can do this even without a resistor. It'll work. Okay. It's not going to harm the diode or LED. However, if we have a 1.5 volt cell like this one, so we have 2 batteries, 3 volts. Now it has a lot more energy stored in there. So current could be higher. And so we want to limit the current that's flowing through. This basically is the operating principle of a flash drive, flashlight. Okay, you have 2 batteries and you have a light bulb. You connect it together. You throw a switch in there. And that's a flashlight. If you have a regular filament light bulb, then you don't need a resistor because the filament itself is going to provide the resistance, right? The operating principle of a filament light bulb is that it opposes the flow of current. And when it opposes the flow of current, it releases energy in the form of heat as well as light. And so while it provides light, an incandescent light bulb also gets hot. So all types of flashlights, I still have one in my toolbox. You have those small filament light bulbs, and you can take that and put it across 3 volt battery, and it'll turn on. No resistors required. These are small experiments that you can perform. In your lab kits, you also have LEDs. So you can take your LEDs and connect it to, I don't know, like a 100 ohm resistor and crank up the supply voltage to like 3, 4, 5, 6, 7, 8 volts. See how bright you can turn it on. If it blows out, I'll give you some new ones. LEDs, I think you have like 1 or 2 in your lab kits. So if you blow one out, just let me know and I'll bring you some. But those are some small experiments that you can try on your own. Okay. Especially, as I said, the coin cell battery, that's like, there used to be some cheap keychain trinkets made out of those coin cell batteries and LEDs. Like you press down on it and it would turn on into a flashlight. Anyway, some real life applications from those kind of circuits. All right, so this are our topics, and this is not targeting the exam. This is more for the final exam. We don't have a midterm in this class. There's no midterm. And as we get in finals week, not finals week, sorry, the final week of classes, I'll talk more about these topics and what is going to be on the final. But since this was already here, I wanted to let students know that superposition is probably one of those questions. Problems that have 1 or 2 or more interrelated tasks, maybe 50-50. Not really certain whether I'll have it or not, so I'm leaning towards both. Reverse engineering problems, for now, I'm not going to have any of those. That could change, and if it does change, you will know during the final week of classes. Basic skills, 100%. 100% on the final exam. Okay. And then problems that are not labor intensive, but could be plug and chug. Typically, plug and chug or plug and solve problems are not something that instructors like to do, but I still see value in those. Plug and solve simply means we have a problem in front of us, there's a system, and we need to decide which equation fits best or which operating principle fits best to solve that problem. Once we are able to assess that and determine that this is the right equation for this problem, all you have to do then is simply plug in the values and solve them. Okay. No other critical thinking skills required. So that's why most instructors do not like to have them on the final, because it's too simplistic. But I still see some value in these kind of problems. So I'll probably have not high stakes, probably low stakes. And then problems which have neither series nor parallel connections, definitely going to be on the final. Now, it's not going to be like 5 problems to test out every single thing separately. It could just be like 2 problems that test out everything. Okay. All right. Let's see what time we have. We have plenty of time. Elementary nonlinear and parametric circuits. So far we have looked at linear resistive circuits comprised of linear resistors. Linear in this case means that the voltage and current for a resistor have a linear relationship. So if voltage increases, then current must increase. If voltage decreases, current decreases, and vice versa. Right? If current increases, voltage must increase. So V is directly proportional to I, and the constant of proportionality is the resistance value R. So V equals IR, Ohm's law. When you have linear circuits, we can apply superposition, Thevenin, Norton, equivalence, everything can be applied equally to the entire circuit. Okay. Then we have nonlinear circuits. In nonlinear circuits, the prime example was a diode. A diode is an example of a nonlinear device because the voltage and current for a diode do not have a linear relationship. And so for diodes, let's draw it out this way. So here's a plot of the diode characteristics. Diode current ID as a function of diode voltage VD. Diodes are 2-terminal devices similar to resistors, capacitors, and inductors. This is something you will, again, look at in 315, which is how a diode is created, the device physics behind it. But in 115, we look at diodes and see how we can apply them towards an application. So diodes, the first thing you need to understand is that the diodes require a certain amount of voltage to turn on. As you can see, before the turn on voltage, there's almost no current flowing through a diode. When you crank up the voltage or the input voltage going into the diode, it starts increasing slowly. And then after the turn on voltage is passed, it increases rapidly. Okay. So overall, the voltage and current have a non-linear relationship. Hence, diodes are non-linear devices. But even in non-linear devices, we can separate out the linear portions of the circuit. So in this case, be the voltage source and the resistances, or the current source and the resistor. And you can still apply linear circuit analysis techniques to that linear portion. Okay, meaning something that contains resistors. Linear portion only. Okay. All right. Parametric circuits. Parametric circuits have a parameter. Okay. So they have a parameter that could change depending on the control at some other part of the circuit. Okay, so the parameter changes in response to a control that's in a different part of the circuit. You're all familiar with this symbol, which is used to represent independent sources. Then we have something known as dependent sources. And in dependent sources can be both voltage as well as current. And so both are listed here. Okay. Dependent sources are sources that supply voltage or current, but they are controlled by a different quantity in some other part of the circuit. And the dependency factor could be on voltage. It could also be on current. So we have a 2x2 cross matrix of dependent sources. Okay. We could have a dependent voltage source that is controlled by a voltage. We could have a dependent current source that is also controlled by a voltage. So a voltage in a different part of the circuit can decide how much voltage or how much current appears in a different part of the circuit. So that would mean this is a voltage controlled voltage source or a voltage controlled current source. If the controlling parameter is a current source, then we could have a current controlled voltage source and a current controlled current source. Okay, all four of those are listed here. For the most part, you will come across them as part of models. So nonlinear devices like diodes, transistors, microchips like op amps, all of those have several different kinds of models. We have different models to account for different parameters and different use cases. Okay. And in these models, we can portray the output as having a dependency on something that goes on in the input side. So in a transistor, for example, in a transistor, we have output current. The collector current is dependent on the base current. So we can have a dependent current source at the output that is dependent on the input base current. And those kind of models are very helpful when we're trying to analyze for circuits and to explain these nonlinear devices. Okay. So, as I said, we have independent sources that are like our regular benchtop power supplies. There are batteries. And then we have dependent sources. Dependent sources are basically sources that supply a voltage or a current, but they depend on their value, some other part of the circuit. If you think about it in a certain way, a voltage divider network is a dependent voltage source. Okay, we have a series resistive circuit. Let's take the example that we had previously, like the 9 resistors. You apply 9 volts to the 9 resistors. What do we have? We have a step connection of like 1, 2, 3, 4, 5, 6, 7, 8, 9 volts, right? We can 9 different output voltages. And each one of them can be considered to be a voltage source, because if you apply 9 volts here, you can apply 1 volt across that resistor. But now, what if I change the 9 volts input to 18 volts? What will happen to my output then? The output that was previously 1 volt. It'll go to 2 volts. So now it is supplying, as a source, it is supplying 2 volts, but it depends on the input voltage. So a resistive voltage divider network can be considered to be a voltage controlled voltage source. Okay. we are looking at the same circuit, but from different perspectives. Okay, we can determine the Thevenin voltage, Thevenin resistance for the circuit, analyze it from that perspective. We can also say it's a voltage, it's a voltage divider network, obviously. We can also say it's a voltage control voltage source because it's supplying a fixed amount of voltage, but it's dependent on a voltage that is controlled somewhere else in the circuit. All right. Okay, this is where I stopped in the previous section. So this is where I will stop in this section too. If you have any questions, feel free to ask. All right, if there are no questions, we'll end class here today. I'll see you here on Friday. Yes. So R2R ladder network, can it be a voltage control current source? Yes, it could. Yeah, because it supplies a specific amount of current. So that's a very good observation. So R2R ladder networks could be a voltage control current source. All right.